Alright, silly people, here's the situation. Uh, we're going to be reworking part of question 2.7. And so, if you're here and you haven't watched my video over 2.7, and for that matter, 2.23 as well, you should go watch those. I'm going to put the link in the description because the results of those are really going to matter for this problem. Um, so what I have here is the wave function for uh, 2.7, and Griffiths is going to tell us to take the derivative of it first. So the derivative of this, just keeping it uh, separate for now, take the derivative of ax, you just get a. I should actually write this here. That's from 0 to a over 2. If you take the derivative of this, you get minus a, and that's from a over 2 to a. But then Griffiths wants us to write it on one line uh, with the expression of the Heaviside function. That is the Heaviside function of x minus a over 2. Let me actually write a better looking theta. Heaviside of x minus a over 2, which is going to be 1 for x greater than a over 2 and 0 for x less than a over 2. That's how the Heaviside function works. So we know that for the x less than a over 2, we want the result to be a, so let's just write a. And then we want it to be minus a when the Heaviside function turns on. So we'll do minus 2a so that it's minus a when it turns on, and it's x minus a over 2, like that. The next thing that Griffiths has us do is take the derivative of this. So the second derivative of the initial wave function, which just ends up being minus 2a times the derivative of the Heaviside function. And we know from problem 2.23 that the derivative of the Heaviside function is the Dirac delta function. So we have a Dirac delta x minus a over 2. Okay. Finally, Griffiths is going to be like, now reevaluate your answer for the expectation value of energy for this wave function in the infinite square well. And so that's going to be the integral psi star h psi dx, where h is the Hamiltonian for the infinite square well, which is just the kinetic energy operator, expanding the definition of momentum. We have minus h bar squared over 2m del squared del x squared. So this is looking more like psi star with a minus h bar squared over 2m out front. And then it's del squared psi del x squared dx. And then we just calculated what del squared del x squared of psi was. So just write that out. It's minus 2a, so I'll just simplify the prefactor by a bit. And you'll get psi star delta x minus a over 2 dx, which means the result of that integral is just plugging in a over 2 into psi star. And so it kind of freaked me out at first, seeing that there were two different wave functions with results at a over 2, but they are, if you plug a over 2 into either of these, you're going to get the same answer because it is continuous. So I'm just going to treat it like it's the first one. So we get h squared a over m times a times little a over 2. So simplifying a bit, it's h bar squared a squared little a over 2m. And then from problem 2.7, this is a normalization constant that we calculated. It was a equals root 12 over a cubed. Right. So plugging that in here, we have h bar squared little a over 2m times 12 over little a to the third. And that simplifies to 6h bar squared over ma squared, which matches our result that we got from question 7 that we did in a different way. So we're all good there.